Okay, so generally in social choice, we need to take a single choice for the whole society. That is, we need to amalgamate, to aggregate a lot of different preferences into a single preference or choice. And sometimes this is almost impossible. In other words, we need to design an outcome that is an equilibrium for the players, so that the players do not have an incentive to lie, to deviate. So in this talk, I will focus on truthful mechanisms, which, thanks to the revelation principle, is equivalent to truthfulness in dominant strategies. So I assume that the players are selfish, and they want to maximize their utility. We assume quasi-linear utilities. It's valuation minus price. And truthfulness means that fix the values of the other players, either their true values or lies. And one player tries to deviate and lie, and he should not have an incentive to do that. He should not be able to increase his utility by doing so. And the most well-known truthful mechanism is the VCG mechanism. So it selects an allocation that maximizes the welfare, and there exists some payment, in this case the second highest bid, that makes it truthful. And the nice thing is that the payments that we give to the players are such that the utility of the players becomes now the social goal, the social welfare. And in fact, we can even generalize it for the case of more items. So this is the VCG mechanism when we have more items. It again chooses an allocation that maximizes the social welfare. And there exist some truthful payments. And we can even generalize it a little more and remain truthful. That is, we can multiply the values of each player by a constant lambda I, and even add an additive constant gamma alpha for each outcome. So the affine maximizer maximizes this weighted sum, this linear transformation of the social welfare set. Okay, so what's more? We know the VCG mechanism. It's nice. Okay, the first result perhaps was a shock to mechanism design because it was an impossibility result. For voting, if there are 3 or more parties and the function is onto, that is, each party can get selected, then the only truthful voting rule is a dictatorship. And you can see Robert's theorem as an extension of this, enabling the mechanism designer to put payments. So you can see it like voting with payments. And again, we have almost an impossibility result. The only truthful mechanisms are affine maximizers. There's nothing else. And the thing we don't like in this theorem, so this theorem is, I'm not hiding any of the restrictions. The only thing we don't like in this statement is the fact that the valuations are unrestricted. That is, each player can report any possible real value as his valuation. So the point is to characterize domains with more restricted valuations. And in fact, a point I liked when reading Robert's proof was that he also gives a very easy way to get the Gibbard-Satterwhite, to get a proof for the Gibbard-Satterwhite theorem by using his own result as a black box. So what he does is basically he says, I proved that the only truthful mechanisms are affine maximizers, that is this weighted sum. And since the players are truthful, they want to maximize their valuation, their utility. But utility is valuation minus payment. If the payments are 0, then the utility is evaluation. So each player wants to maximize its valuation. And the mechanism, the only possible mechanism is to maximize this weighted sum. So the lambdas and the gammas has to be 0 for all players except for 1. So that's a way to get the Gibber-Satterwhite theorem from Robert's theorem, using Robert's theorem as a black box. So this talk is going to be about getting theorems, one theorem, one characterization proof as using another characterization proof as a black box. Okay, so of course, unrestricted valuations are unrealistic, so we would like to characterize more realistic domains, like different kinds of combinatorial auctions. And a question I really like is one post by Ron Levine, his chapter of the AGT book, which says that how much do we need to restrict the domain in order to admit mechanisms that are different than affine maximizers. And I would also like to see the same proof working for different domains, because there are a lot of similarities in these proofs. And even better to use to take the theorem as a black box and to get another characterization for the characterization for another domain. Okay, you all know what the combinatorial auction is, and buyers and items for sale. I assume that that we allocate all items. The players are selfish, and you will ask me what the objective is. I don't care about the objective. I want to characterize all mechanisms that are truthful. So to find all possible mechanisms regardless of objective. So for the case of two players, the Roberts domain can be seen like you have 4 different say you have 4 different outcomes. Then Roberts domain is given by the valuations of both players. So you can see the domain as a matrix, where you have the rows are the players and the columns are the different outcomes. And then combinatorial public projects can be represented similarly. In this case, again, the outcome is the same, but it's like having two items. But the outcome is the same for both players. And then combinatorial auctions, the allocations are complementary. So if one player gets nothing, then the other player gets both items, and so on. When denoting the domains in this way, each one, the way I describe the series I describe them, also gives an inclusion. So the unrestricted valuations are a subset of combinatorial public projects. The domain of unrestricted valuations is a subset of the domain of combinatorial public projects, and this is a subset of combinatorial auctions. And the last thing in the inclusion is additive combinatorial auctions. This is like the most restricted valuation you can have. Some common restrictions on evaluations are these. I'm basically going to talk about the two-player case, and hopefully this can be. I hope this might be extendable to the n-player case as well. Actually, two-player or two-player with less monotonicity. And the way I like to think of the domain is like if the valuation could be the valuation. So I fix the values of all other players, and I have player 1, say, and this is his valuation of for getting the first item. This is his valuation for getting the second item, and this is his valuation for getting both items. And if, for example, I assume that the valuations are additive, then I just allow for this slice of the whole cube. So these are the possible valuations. And the question is, if I know that if I know the characterization for this domain, what can I say about the bigger domain? So I know the most difficult, say, proof, and I want to find the proof for the bigger domain. So an intuition, why did I say the most difficult proof? An intuition behind that is that the richer the domain is, the bigger the input space is, and then the more restrictive becomes truthfulness. So the fewer are the possible algorithms, and the less difficult is the characterization. And if you're looking for an algorithm, it should be sort of the other way around. So it should be easier to construct an algorithm for the case of additive valuations. But we should be careful. We want a rigorous proof of this intuition. So let's start some broken proofs. So the first thing when one sees all these different domains, first says, okay, we have to give a different proof for each domain, and perhaps get some ideas from one to the other. But that's all. Then perhaps you might think it's obvious. So you say, okay, you take a subset of the possible valuations, subset of the input. You show that the only truthful mechanisms are affine maximizers. Then the possible mechanisms for a bigger domain are also affine maximizers. But this is not the whole. This is not the whole proof. This is not the correct proof, because this just gives that the restriction of the mechanism to the smaller domain is an affine maximizer. That is, we don't know if the mechanism is an affine maximizer for the whole domain. Okay, so these are some characterization theorems I would like to unify. So first is Robert's theorem. For at least 3 outcomes, the only truthful mechanisms are affine maximizers. Then there is a characterization of truthful combinatorial auctions. Actually, the additional, for the 2-player case, the additional restrictions are not needed except for decisiveness. And also some special cases of combinatorial auctions like subadditive combinatorial auctions. Okay, so what we need is, suppose that V is a subdomain of the 2-player combinatorial auctions. If the only truthful mechanisms for the subdomain which are decisive are affine maximizers, then the same holds for every superdomain of V. Actually, I can drop decisiveness here, but I cannot drop decisiveness in the characterization. Sorry, this is a mistake. Sorry, subdomain is a subset, but you have to think of the domain as these matrices, right? The domain. I represent the domain by these matrices, where there is one row for each player and one column for each outcome. I assume a finite number of outcomes, but if you, I mean, all these problems do have such one, right? And a subdomain is, yeah, exactly, you take a subset of the possible valuations. Any subset, yeah. Actually, yeah, the proof is really simple. But it has to be an affine maximizer, right? So I cannot prove it if the characterization involves some other mechanism. So the fact that the mechanism is an affine maximizer, makes the proof easier.
So is the S-mon here, that sort of implies that all items are allocated? Is that, you really need that as part of the reduction?
I can get this theorem for 2 players or for n players, assuming S monotonicity. My intuition says that it should hold also for n players, generally, but I can't prove it.
For 2 players, you can get it even without allocating all items?
No.
Or you need to allocate all items?
I need to allocate all items, yeah. Yeah, that would be great. Okay, so we would like to apply this theorem and use additive combinatorial elections as a subdomain, because this is the most restricted subdomain we know. But the problem is that the characterization for this domain is in terms of not only of affine maximizers, but also of threshold mechanisms. So we have to find a way to reason why threshold mechanisms do not make sense in any domain other than the additive domain, in any domain that is has slightly more complicated evaluations. So my black box will be this characterization for 2-player. It was written for 2-player scheduling, but since it's regardless of objective, 2-player scheduling is the same thing as 2-player additive combinatorial elections that allocate all items, though. So the decisive truthful mechanisms, the characterization is that the decisive truthful mechanisms partition the items into groups, and the items are either allocated by threshold mechanisms or affine maximizers. Okay, so the scheduling problem, probably you know it. The idea why the 2 problems are the same is that in auctions you want to allocate, to sell the objects to bidders who value them high, and in scheduling you want to allocate the tasks to machines with small processing times. But you can change max to min since the objective of the 2 problems is different, but I don't care about the objective, I just care about all possible mechanisms, right? So this is basically, scheduling is basically a combinatorial election where you don't need the valuations for getting both items because it's additive. And yeah, the threshold mechanisms that are involved in the characterization are the following kind of mechanisms. First, let's see what I call task independent or item independent. The rows are the players and the columns are the items. So an item independent is a mechanism that allocates the second item looking just at the values of the second row, of the second column, sorry. And then a threshold mechanism does something slightly more complicated. So in order to allocate, to decide what is A12, it uses all the spread values. So it doesn't look just at the column, but it looks at the values of other players for the same task and not the values of player 1 for this item. And if you want to draw it, if this is a valuation for getting the first task, the first item, and this is a valuation for getting the second item, sorry about the T's, then the threshold mechanism look like that. That is, the threshold is independent of the allocation, whether the player gets or not the second item. Okay, so something we need is that if we have a characterization for a domain D of valuations, represented in the way we say this matrix representation, if we take the matrix and multiply the whole matrix by a lambda, and also add a delta, then there is a bijection between the characterization of the domain D and the translated domain, the transformation of it. Another way to see threshold mechanisms is that the payments are additive. That is, For the case of additive valuations, the payment for an allocation is the sum of the payment for getting each one of the items separately. And for the translated domain, it is not hard to show that the payments are like that. This is the delta we used in the additive constant, and this is sorry. This is This is basically not the constant. It's a vector, and you can have one delta for its allocation. Okay, so the idea is to take the domain of additive valuations, for which the possible mechanisms are the threshold mechanism and the affine maximizers, and to also take a small perturbation, say, of it. That is, we allow additive plus a small constant delta. And this will enable us to vanish the threshold mechanism. So threshold mechanisms do not make any sense, are not truthful anymore, if you take this, the union of these two domains. And actually, we need to do this thing just for one of the players, and the other can remain and have additive valuations. It is easy to see that if you just add some constant delta, a small constant delta, you can make this domain a subset of subadditive, superadditive, or submodular combinatorial options. This proves that, in some sense, scheduling is the translation domain, where that admits some mechanisms that are different than affine maximizers. But that's just for the case of two players then. So it would be very interesting to generalize this approach for the case of more than 3 players. But then the problem is that for more than 3 players, or even for 2 players, when we don't allocate all items, we don't have a lot of characterizations. Also, we are not sure if the only possible mechanisms are the affine maximizers. So maybe they admit more mechanisms. And finally, I would like to say a few words about another paper. Just the 2 slides, don't worry. So this is about revenue maximizing mechanism design. You all know the classical result by Myerson, where you have a single item for sale and n bidders. The valuations of the players are drawn from publicly known distributions. And the goal is to maximize the revenue of the auctioneer. And again, it turns out that even though we look at Bayesian mechanisms, at Bayesian equilibria, and not in dominant equilibria, which is a much stronger notion, then again, the Vickery mechanism is the optimal mechanism, but we also need a reserve price. So it's like this talk is about saying good things about the Vickery mechanism. No. For the case of Bayesian combinatorial auctions, we add the restriction that each player has a public budget, and the items that the player can pick should be a Matroid. And we want to find the optimal mechanism, that is a revenue maximizing mechanism, or an approximately optimal mechanism. And the Matroid constraints we consider are the following. We consider both universal and individual Matroid constraints. In universal Matroid constraints, the set of items allocated to all bidders has to be an independent set. And in individual Matroid constraints, for each player I, the set of items allocated to him should be an independent set in the Matroid, in his own Matroid. So the work the model, we use the same model as the second paper. Yeah, this is a table of some of the results. So we give a sequential posted price mechanism that achieves some improved approximation ratios or approximation ratios for classes of matrices that were not known. That's all.